Very good. Adiabatic process. What is an adiabatic process? A thermodynamic process in which no heat energy is exchanged between the system and the surroundings. Such a process is called adiabatic process. Heat energy should not enter into the system, and also heat energy should not go out from the system. Okay? Such a process is called an adiabatic process. So a process should be adiabatic if it is carried out in an adiabatic walled cylinder or non-conducting walled cylinder. If the system is taken in a non-conducting walled cylinder, the system will not give its energy to the outside surroundings, and also system cannot absorb heat from the surroundings also, because the wall is non-conducting or adiabatic wall. Okay. Another condition is that if the process is a quick process, I mean sudden compression or sudden expansion, then system will not get enough time to exchange the heat or adjust with the heat energy variations. So all the sudden processes are called adiabatic process. For example, I could say flattening of an automobile tire. It is having a compressed air in it. If it blasts all of a sudden, the time taken for the heat exchange will be almost zero, therefore no heat exchange is possible. So that flattening of the tire is considered as an adiabatic process. And another system we can consider that the thermos flask. Thermos flask is not allowing the heat energy to go outside, or no heat exchange is allowed between the system inside and the surroundings. Okay. So when we apply the first law of thermodynamics to the adiabatic process, let us see what are the conditions possible. First law says that the heat energy given may be used up in increasing the internal energy and also for doing external work. So I can write this as Q, heat energy given, will be equal to delta U plus P into delta V. Okay. So if it is an adiabatic process, no heat exchange is possible, that the heat energy given to the system or taken out from the system is zero. Therefore, we can have delta U plus P into delta V is equal to 0. So, two conditions possible. One, delta U equal to minus of P into delta V. One situation. Second one is that P into delta V is equal to minus delta U. This is the second situation. Now let us consider the first situation, equation 1 that we consider. Here the negative work done is coming. So actually negative work done relates with the volume decrease. So when this volume is decreasing, you can say change in volume is negative. So volume decrease is possible with the compression. So pressure will decrease in volume. There is a sudden compression is coming. So when the gas is compressed suddenly, then the internal energy is increasing. This is the positive value here. So changing internal energy positive means internal energy is increasing. So sudden compression of the gas gives an increase in its internal energy. That means the gas is getting heated up. Internal energy increase means that there is a heating is coming. So sudden compression gives rise to heating of the system. Okay. So adiabatic compression heats the system. First equation says that. So the same way, if you consider the second equation, here the work done is positive. That means the change in volume is positive, means that the volume is increasing. Volume increasing means that expansion. If the sudden expansion is coming, then internal energy goes negative, means that change in internal energy negative. That means that internal energy decreases. So internal energy decreases means that the gas is getting cooled. So in another way we can discuss this as the gas expands by itself using its internal energy, therefore internal energy decreases, using that the expansion is coming. So sudden expansion cools the gas. So adiabatic expansion cools the gas, adiabatic compression heats the gas. So sometimes you might have come across a statement like this, that it is possible to heat a gas without really heating it. That statement is associated with this first condition. You are not heating it, but you are just compressing the gas suddenly, so gas is getting heated up. So that statement holds good for this particular case. Okay? So adiabatic expansion and adiabatic compression causes heating and also cooling of the gas. Clear?